Everyone assumes massive chains hold 200,000-ton ships at dock, but 99% of the world's fleet uses ropes instead. Not steel cables, not magnetic clamps, simple ropes. It sounds impossible until you realize chains have a fatal flaw that makes them useless for ships this size. The answer lies in a single physics principle that most people never consider. Here's why flexibility beats brute strength when the stakes are this massive. The physics principle is elasticity. When a 200,000-ton ship sits at dock, it's not just sitting there, it's breathing. Every 6 hours, tides push water levels up and down by several feet. Every wave that hits the hull transfers thousands of pounds of force. Every container loaded or unloaded shifts the ship's center of gravity. A rigid chain can't absorb these forces. It snaps under sudden load spikes. But a rope flexes. It stretches just enough to absorb the shock, then returns to position. Maritime pilot Jeffrey Harmer puts it simply: chains have low elasticity and break under excessive force, while ropes counteract tides and waves through controlled flexibility. Think of it like tying down a massive living animal that needs to breathe. Chains would strangle it. Ropes let it move just enough to survive. This is why 99% of commercial ships, from small cargo vessels to 400-meter megaships, rely on rope-based mooring systems. Even with magnetic plates and mechanical levers available as alternatives, the maritime industry chooses fiber over steel. But here's what most people don't realize. These aren't just any ropes, and they don't work alone. The system that keeps a floating skyscraper motionless requires 6 strategic lines, each with a specific job, working together in perfect tension. The 6-line system is maritime engineering at its most elegant. Each rope has a name, a position, and a critical function that prevents the ship from moving in any direction. The headline runs from the bow straight to the dock. It stops the ship from drifting backward. The stern line does the opposite from the back of the ship. But forward and backward movement is just the beginning. 2 breast lines run perpendicular from the ship's sides directly to the dock. These prevent the ship from drifting away from or crashing into the pier. Without them, even a gentle wind could push 200,000 tons of steel into the dock with catastrophic force. The real genius lies in the spring lines. The forward spring runs at an angle from the bow toward the back of the dock. The aft spring runs from the stern toward the front of the dock. These diagonal ropes prevent the ship from sliding forward or backward along the dock's edge. 6 ropes, 6 directions of control. Together, they create a web of tension that locks a floating mountain in perfect position. But deploying these lines requires serious hardware. Mooring winches mounted on the ship's deck do the heavy lifting. These motor-driven drums, powered by electrical or hydraulic systems, can generate thousands of pounds of pulling force. No human crew could manually tension a rope holding back 200,000 tons. Shore workers catch the rope ends thrown from the ship and loop them over bollards. These aren't just any posts. They're massive steel fixtures anchored deep into the dock's foundation, engineered to handle forces that would tear apart normal infrastructure. The process looks choreographed from a distance. A maritime pilot boards the approaching ship to guide the docking procedure. Tugboats push the vessel into position. Deck crew operates the winches, while shore workers handle the bollard connections. Every movement is coordinated because one mistake could send the ship drifting into the dock or other vessels. What makes this system work isn't just the ropes or the hardware, it's the constant human oversight. Throughout the ship's stay at dock, crew members walk the deck checking line tension. Tidal changes and cargo operations constantly alter the forces on each rope. The crew adjusts tension using the winches, keeping each line in perfect balance. This isn't a set-it-and-forget-it system. It demands active management every few hours, around the clock, for as long as the ship remains moored. Modern synthetic ropes have revolutionized this ancient system. Companies like Samson Rope have over 14,000 high-performance synthetic lines currently in service worldwide. These advanced fibers equal the strength and durability of steel wire while requiring fewer crew members and shorter mooring operations. The synthetic materials also address another critical advantage. They're lighter and easier to handle than traditional steel wire, reducing the physical demands on dock workers and ship crews. But even with these advances, the fundamental principle remains unchanged. 99% of ships still rely on rope-based mooring because the physics of elasticity cannot be replaced by automation or stronger materials. However, this elegant system carries a hidden danger that makes it the most feared equipment on any ship. The very elasticity that makes ropes superior to chains also makes them potentially lethal. When a mooring line snaps, it doesn't just break, it recoils. A mooring rope under tension stores massive amounts of potential energy. When that energy releases suddenly, the rope becomes a projectile. Maritime experts describe the recoil force as striking with the power of a cannonball. For anyone in the path of a snapping mooring line, the impact is often fatal. This danger isn't theoretical. It's a documented hazard that has claimed lives in ports worldwide. The same elasticity that allows ropes to absorb tidal forces and cargo shifts can turn them into weapons when they fail under extreme stress. Crews train extensively in snapback zones, the areas around mooring lines where recoil could occur. These invisible danger zones extend far beyond what most people would consider safe distances. A snapping rope can strike with lethal force dozens of feet from its anchor point. The industry has responded with safety innovations. Quick-release mooring hooks reduce the need for port staff to manually handle heavy ropes. Load monitoring systems provide real-time data on rope tension, warning crews before lines approach their breaking points. Advanced synthetic ropes are designed to reduce recoil energy compared to traditional materials, but these safety measures can't eliminate the fundamental physics. Every mooring rope is a compressed spring holding back forces equivalent to a natural disaster. The moment that spring breaks, it releases energy with potentially deadly consequences. This is why the mooring process requires such precise coordination and constant vigilance. It's not just about keeping the ship in place. It's about managing a system where failure doesn't just mean property damage. It means human lives are at stake every time a 200,000-ton vessel ties up to dock. Despite these dangers, the rope-based system persists because the alternatives are even riskier. Chain failures are sudden and catastrophic. Mechanical systems lack the flexibility to handle dynamic ocean forces. Magnetic systems remain untested at the scale required for megaships. The maritime industry continues using ropes not because they're perfectly safe, but because they're the safest option available for holding floating cities against the relentless forces of wind, waves, and tides. As of January 2026, the rope revolution continues accelerating. Samson Rope's 14,000 synthetic lines in service represent just the beginning of a materials transformation that's reshaping how the world's largest vessels stay secure. These aren't your grandfather's hemp ropes. Modern synthetic mooring lines use ultra-high molecular weight polyethylene fibers that outperform steel wire in almost every category. They're lighter, stronger, and generate less dangerous recoil energy when they fail. The synthetic revolution means smaller crews can handle larger ships with greater safety margins. But the real breakthrough is happening in the monitoring systems. Companies like Trelleborg now integrate load monitoring technology directly into synthetic ropes. Sensors embedded in the fibers provide real-time tension data to the ship's bridge. Crews can see exactly how much force each line is absorbing and receive warnings before dangerous load spikes occur. This technology transforms mooring from reactive management to predictive control. Instead of crew members walking the deck checking lines by feel, digital systems track every pound of force across all 6 mooring positions simultaneously. When a tide change or cargo shift creates dangerous tension in one line, automated alerts give crews time to adjust before catastrophic failure occurs. Quick-release systems are becoming standard at major ports worldwide. These mechanisms allow shore workers to disconnect mooring lines remotely, eliminating the need to approach bollards when ropes are under extreme tension. The oil company's International Marine Forum now recommends quick-release hooks for all high-risk mooring operations. The result is a system that's simultaneously more automated and more human-dependent than ever before. While technology provides better data and safer handling, the fundamental requirement for human judgment and coordination remains unchanged. Maritime pilots still board approaching vessels. Crews still monitor and adjust tensions around the clock. Shore workers still coordinate the complex dance of positioning 200,000 tons of moving steel. Yet even with all these advances, the basic physics haven't changed. 99% of the world's commercial fleet still relies on the same six-line rope system that secured ships for generations. The principle of elastic tension under dynamic load remains the only practical solution for holding floating cities against oceanic forces. The persistence of this seemingly primitive technology reveals something profound about engineering excellence. Sometimes the most advanced solution isn't the newest technology or the strongest material. It's the approach that best matches the physics of the problem. Ropes work because they embrace flexibility instead of fighting it. They absorb force instead of resisting it. They bend instead of breaking. In a world of constant motion, adaptation beats resistance. This principle extends far beyond maritime engineering. The most robust systems in nature and technology share this characteristic. They respond to stress by flexing, not by becoming more rigid. Trees bend in windstorms. Suspension bridges sway during earthquakes. Successful organizations adapt to changing conditions rather than maintaining inflexible structures. The next time you see a massive ship at dock, look for the six lines holding it in place. Notice how thin they appear compared to the vessel's enormous bulk. Those ropes represent more than just practical engineering. They demonstrate the counterintuitive truth that sometimes strength comes from the willingness to yield. Understanding this hidden infrastructure changes how you see the modern world. Every container ship delivering goods to your local stores relies on this delicate balance of tension and flexibility. Every cruise ship, every cargo vessel, every floating platform depends on ropes that most people never notice or consider. The engineering is invisible until you know where to look. Then it becomes impossible to ignore. What other weak solutions in your daily life might actually be stronger than the obvious alternatives? Subscribe to discover more hidden engineering that challenges everything you thought you knew about strength, safety, and the systems that keep our modern world functioning.